Stop sign. Born a sin, they told us always been in the top crime. In our held lives, the rise is a rock climb. Even though they frisk you for the pistol, I got mine. Official when I pick.
2A, we're going to start with vectors, specifically vectors in the plane. Okay, so basically, a vector in the plane, hold on, let me get a straight line here. There we go, that's better. So I'm just going to draw a few vectors. You guys have probably seen these before, maybe not in detail or anything. But I'm just going to draw a couple here, just to introduce you to vectors and what are they. Okay, so here's one. We'll make this end right here. So here's a vector, right? And here's its base. This one is based at the origin, which is 0, 0. And it finishes up at 2, 1. Okay, so this is, we're going to call this vector v. Okay, and I'll draw another one as well. So we'll base this one at the point 1, 2. So this is its base, and it's going all the way to 4, 4. Alright, so I'm going to draw it ending up right there. Okay, this is like a connect the dots game. Okay, so here is the tail of the vector, like the base, right? And here's the head, where it points to and ends up. And I'll call this one W. Alright, so first of all, what is a vector? A vector is defined as kind of a quantity that, or a measurement, or an object kind of thing, that has two components, or two parts to it. The first is it has a magnitude, and that basically refers to its length. Okay, so the length that we see here would be its magnitude, like this. This length here would be the magnitude of W, and this length here would be the magnitude of V. Alright, and the second thing, the other part of a vector, is that it has direction as well. Okay, and whenever I think of, I remember when I was learning vectors, I'd seen the movie Despicable Me before I learned about vectors, so my mind would always jump back to the guy in the orange jumpsuit thing. Anyways, so yes, the second part of a vector is its direction, which I think happens to be the, not necessarily the most important part, but definitely it holds its own, because the direction is how we name a vector. So it tells us how to name a vector. How to name a vector. For example, the way we would name vector v here, so this one down here, is not based on where its tail is or where the base is, which is at the origin, but it's based on in what direction is it moving. How many units in the x direction and how many units in the y direction. And here there are only two components, the x and the y component, because we're only in the plane, which means, so plane refers to 2D, right? Plane refers to two-dimensional thing. And space, just for future reference, space refers to three-dimensional, okay? So right now we are starting in the plane, okay? So we only have these two components, so we're going to see, if we look at vector v, how many units does it move in the x direction? I guess it would be pretty helpful if I labeled the axes here. Okay, so here's our x along the bottom and our y-axis. So along the x-axis, our v vector moves 2 units. It makes 2 jumps, right? So we're going to put a 2 here. And then our y, it goes up 1 unit in the y direction. Okay, so this is how you name vectors, by their direction. So vector v is going to be 2, 1, and we denote them with little arrows to show that they're a vector. Okay, so now let's practice with naming w. So even though W is based at a different point other than the origin, it's based at 1, 2, point 1, 2, we're just concerned with how much it moves in the x direction from its base point and how much it moves in the y direction. So here, if we draw a little line, so it starts at the x value of 1, but then it goes all the way over to 4, right? So it actually moved 4 minus 1 units, so that would be a 3. So our x value is going to be a 3 here. And our y, it starts from the level of 2, right? And it moves up 2 units to become 4, right? Because this point is 4, 4 here. All right, and so it moved from 1, 2. So basically, so this again is 2, so we're going to have 2 as the second component. Basically, what a vector, in more simplistic fashion, I guess, you could say a vector is kind of naming the components that give you the slope. So if you see here, you see how this, I drew this triangle, and if you take rise over run, if you take your y value over your x value, you get the slope of your arrow. Okay? Alright, now moving on. So now we'll go over a pretty simple concept of parallel vectors. Okay? So parallel vectors basically means what it sounds like. Whether vectors are parallel or not, whether they have the same slope. Okay, so I'll draw a couple vectors here, alright? So I'll have that, and here's another one. Hold on here. Let me get that going in the same direction. Okay, and then we have one like that, and another one, we'll do D, that, E, be like, actually, hold on here. Okay, almost there, and I'll do one more for you guys. Alright, so here we have an assortment of 6 different vectors, alright? And parallel vectors basically just mean that they lie along the same line, basically. So here I drew A and B, and these ones, even though my drawings might not be exactly to scale, A and B are going to be parallel, okay, because they lie along the same line. They're never going to intersect, all right? So vector A is parallel to vector B, okay? Let's check vector C. This one has a completely different slope, so C is out. How about D? No, that's almost a vertical line there, so that one's out. E, let's see, this one is actually pointing in a different direction, right? Because A and B were pointing up and to the right, and E is pointing down and to the left. But that doesn't really matter in the case of naming parallel vectors, just as long as it lies on the same line. So these two, A and B, are also going to be parallel to vector E. And lastly, let's check vector F. This one will also be parallel. So all 4 of these are parallel to each other. Just E here, this one's flipped around, so this gets a special name, and it just is called opposite because it's pointing in the opposite direction, in the negative direction. Okay? Alright. Okay, so now what we're going to do on this slide is actually kind of combine the concepts that we've learned so far. Alright? So again, I'll draw a couple vectors here. So we have 1, 2, 3, and 4. And then 1, 2, 3, 4. Okay, let me get this set up. And we'll have one base at the origin again. And then it'll go to this point here. I'll end up there, so at 2, 1. And then I'll have another vector, based at 1, 2, and going to 3, 3. Alright. So it looks like, oh, I missed the line, hold on. I need a ruler for this thing. Okay. So we have another one there, and I'll call this bottom vector here V, and I'll name this one R. Okay, R arrow. Alright, so the important point here is that, first of all, we see that these two, if we were to draw a line through them, they follow through, or they lie on 2 lines that are actually parallel to each other. So V, the vector V, is going to be parallel to R, and we can verify this not only by eyeballing it, because sometimes things get a little bit more complicated than meets the eye. But if we were to actually name each of these vectors, let's do V first. So it moves 2, again, here's our X and here's our Y. It moves 2 units to the right on the X axis, so 2, and then it moves up 1 on the Y, so positive 1. And let's check what R is. R is going to be, it starts at 1, X value of 1, so this is 1, 2, and it finishes at 3, 3. So we can actually get our components by subtracting the endpoint from, the endpoint minus the start point, or the base point, okay? So we're going to do 3 minus 1, comma, 3 minus 2. And we actually get the same things, 2, comma, 1. So these are the same components as vector V, but you see how even though these are exactly the same, our vectors, when we actually look at them on the xy plane, they look different just because they have different base points, okay? But since the naming part, since these are exactly equal and they depend only on the direction that the vector is pointing in, they have the same direction and exactly the same magnitude, right? So these have same, and I'll just abbreviate here, magnitude and direction. So here's our conclusion. So we can consider them equivalent, okay? Equivalent. And the big takeaway from this, why this is so important, is that what we can do is actually what's called translate them. So these are, I'll just put translation. And whenever you see the word translation, that just means taking whatever you have and moving it. Not like rotating it or flipping it around, but you simply shift it or slide it on either on the plane or in space, wherever you're working. So here, the takeaway idea is that we can translate any vector. So like, for example, let's say we're looking at R. You can ignore V right now. We're looking at R, which has the coordinates 2, 1 right here, okay? And we want to make our lives easier, basically, by shifting its base point to the origin. So we're going to move all of this down here, okay? So if we shift it, then we actually end up getting what is equivalent to vector v. And it'll end up having the same components, right? Because the direction didn't change or anything. We didn't turn it around. We didn't rotate it at all. We just shifted its base point, but it's still pointing in the same direction, okay? All right. Now on to components of the vector. So components of vectors. Okay, so again, I'm going to draw a little picture here. 1, 2, 3, 4. 1, 2, 3, 4. And this time I'm going to name my axes first, so don't forget. 1, 2, 3, 4. And 1, 2, 3, 4. Okay, so this vector is going to start at 1, 1. So this is its base point. And I'll name it P is the point 1, 1. Alright, and it's going to finish at 4, 2. Alright, and this is going to be the point Q. So this is 4, 2, all right, and it's pointing like so. All right, so again, I kind of briefly went over this on the last example, but let's say v is equal, the vector v, so p and q are just points, all right? So p is just this point here existing by itself, and q is just this point existing by itself. The arrow part is what I'm going to name v, and v, the vector, is the vector pointing from P to Q, all right? And how you figure out the components here, in a more official, formal way, is taking the endpoint coordinates and subtracting away the start point, or the base point coordinates, okay? So we're going to start with 4. This is like your x coordinate of Q, and here's your y coordinate of Q, and this is your x coordinate of P and y coordinate of P. So we're going to do xq minus xp, so that would be 4 minus 1. And then the second, to get your y component for your vector, you do 2 minus 1. Okay, so this is our xq minus xp, and then yq minus yp. And again, q is your finish point, or your end point, and p is your base point. Alright, so then ultimately we just get the vector v is going to be equal to 3, 1. Okay? And again, this tells you, if you were to draw like the little lines for slope, this would tell you rise over run if you were to do the y divided by the x component. So this has a slope of 1 over 3, just if you're curious, basically. Okay? Alright, so now the second thing I want to do with this vector v here is calculate its magnitude. So I'm going to show you magnitude of v. It's denoted by like a double vertical bars on each side. So magnitude is equal to the length. So what we're going to compute now is how long is this vector. Okay? And the way you do that is you take its components, so each of the x and the y, we're going to square them, okay, add them together, and then take the square root of everything that we calculated. Okay? So if we just plug these in, we're going to do 3 squared plus 1 squared, all under the square root symbol, and this comes out to the square root of 10. Alright? And this gives us the length of vector v.
I'm supposed to be good, whole hood doing dirt. I know the woes of foot soldiers pouncing in step. Been vet, never bounced a chin check. The fact that one is stacked made me sling.